Next in this series of RL circuits I'm solving for you is 2005 E2. It's a nice problem involving two resistors here and an inductor here in parallel with R2. My initial advice for this problem, just like it was for the last one, is to spend a little bit of time before you even read the problem just conceptualizing this circuit and thinking about what the switch does and how the inductor behaves. Pretty obviously, if the switch is open in this particular problem, nothing interesting is going to happen, so we don't have to think about that very much. But it is interesting to think about what happens when the switch closes in terms of the initial behavior of the inductor and the long-term behavior, the steady state behavior. So when this switch is first closed and current begins to flow inside this circuit, the instant that the inductor sees a potential difference across its terminals, which it's going to have because of the current flowing through R2, it's going to respond in such a way that it prevents any current from traveling through it initially. On the other hand, after a long period of time, and this inductor has become accustomed to the current running through this circuit, it's no longer going to respond at all, and it's essentially going to short out R2. And so, typically, when you're given these problems, you're asked things about what happens to the current initially and after a long period of time. You're asked to graph things like the current in one of the components or the potential difference across one of the components. And we've got all of it conceptually laid out right here. Sure enough, the first thing being asked in this problem is what the current is at time t equals 0 when the switch is closed. So all you got to do is ignore the inductor because it's not doing anything except preventing any current to flow through it. So you just have two resistors in series, and the total current is the EMF of the battery divided by their combined resistance. And as expected, you're asked for the current after a long period of time, after the inductor is acting as a short. So this part is pretty straightforward. You start with a rather small current because both of these resistors have to have current going through them, and you end up with a little bit larger current as R2 starts to be shorted out. I got a little bit ahead of myself. That was part C that was being asked for here. So I'm going to take a step back and do part B, which is where it asks, what is the rate of change of current in the inductor at time t equals 0? What's kind of interesting about the way that I solved this was that initially I got a value that looked kind of different from what the problem solution gave from College Board, and I realized I had to do a little bit of algebra to show that they were the same. The College Board solution was, in my opinion, more elegant because it required one fewer term in the Kirchhoff loop rule, but I'll show them both because it's nice to see how no matter which loop you choose, as long as it's got the inductor in it, you've got to get the right answer. They took advantage of the fact that because these two components are in parallel, they've got to have the same voltage. And so if you take the current that's running through R2, which is given by this, then you simply multiply the current by R2. So I spent a couple minutes being confused because my algebra skills have gotten rusty, I guess. And I had to take a minute to reassure myself that I didn't do it incorrectly, that these were the same answer. If you want to see that, I'll do the algebra over here. Finally, the last question says that after the circuit has reached its steady state current value of EMF over R1, the switch is opened. Now, because this is an inductor, all does not go immediately to zero the way it would if this were purely a resistor circuit. Some things continue to happen even after the switch is opened, which is kind of interesting. In fact, one of my favorite demos of the whole year, I don't get to do this year, and involves pretending that I set up a circuit for you guys to see, and then it doesn't work right, and then I open the switch, I turn it off, and it works. And I kind of pretend to be confused. Anyway, all we have to do is think about what was going on in the inductor at the instant the switch was opened, which is that the inductor had this current running through it, and then say that that's initially what goes on inside R2.